Okay, so now let's discuss the longest increasing subsequence problem. I know this is typically framed as a dynamic programming problem, but this can also be solved. I mean, any problem that is solved using dynamic programming has a recursive, is solved using recursion. And in fact, we are going to work our way up to dynamic programming. But first, we want to start off with solving this LIS problem using first vanilla recursion, then backtracking, and then in the next lecture we will discuss dynamic programming like that. Okay, very important to go build up from very basic to more complex algorithms. Okay, so let's talk about sequences. As you learned in the earlier part of the course, a sequence is a ordered list of of elements, I should say. Typically, it's a number. Typically, each of these are numbers, and a subsequence is a a subsequence is a subset. There we go. Is a subset of the original sequence, where the order of this subsequence respects the order of those elements as they appear in the original sequence. Okay, so if we had a sequence that was 1, 2, 3, 4, 5, 6, then a subsequence of these could be 2, 3, 4. It could be 2, 3. It could be 1, 5, 6. It could be 1. That's it. Okay, so a subsequence is simply some elements of the original sequence. They don't have to necessarily be right next to each other. That's a substring. The elements don't really have to be right next to each other. They simply have to respect the order of how the elements appear with respect to one another in the original sequence. Okay, all right. So that is a subsequence, and a subsequence or a sequence is increasing if each of the elements is less than the other. Okay, and we're saying that this is strictly increasing. And it is non-decreasing if each of the elements is less than or equal to the next element. Okay, so there's a difference between increasing and non-decreasing, although I've heard both these terms used interchangeably, honestly. The best thing to do is, if you're asked this question on an interview, just really ask the interviewer to clarify. Okay? Okay, so as an example, we have a sequence 6, 3, 5, 2, 7, 8, 1, 9. And a subsequence of the above is 5, 2, 1. A increasing sequence is 3, 5, 9, 17, 54. A decreasing sequence is 34, 21, 7, 5, 1. And an increasing subsequence of this sequence is 2, 7, 9. 2, 7, 9. It is a subsequence of this sequence because the order of 2, 7, and 9 is respected. And it is increasing because 2 is less than 7 and 7 is less than 9. Okay. So here's our problem. We have a sequence of numbers, an array. Okay. And our goal is to find the increasing subsequence of maximum length. Okay, otherwise known as the longest increasing subsequence. Okay, so what do we do? Well, first, let's consider what the longest increasing subsequence would be. For example, in this sequence, 6, 3, 5, 2, 7, 8, 1, you have multiple increasing subsequences. You have 6, 7, 8, 3, 5, 7, 8, 2, 7. But the longest increasing subsequence there's only one. It is the 3, 5, 7, 8 subsequence. Okay. So, how do we solve this problem? Remember, in life, sometimes the best way to solve a problem is not to get bogged down in how to solve it perfectly or optimally right off the bat. Maybe the best thing to do, first step, is just to solve it some way. Okay? So, what is the most basic solution to this problem? Well, let's see. We know the problem is asking us to find the maximum subsequence, the longest subsequence. So maybe we just find all the subsequences in the array, and then we just look to see which one has the greatest length, right? So that's exactly what we do here. We enumerate all the possible subsequences of A, and then we look and then we search through them. If this subsequence is greater than the subsequence we've already seen, then the max is equal to that subsequence. Otherwise, we ignore it. Okay, and then we output the max. So, does this work? Well, yeah. I mean, why wouldn't this work? We look through all the possible subsequences and we're just picking a maximum value. The same way that if we wanted the maximum element in an array, we just go through the whole array and have a little temp variable that stores the maximum value. So of course this would work. The question is, what's the running time? Okay? The question is, what's the running time? Well, it really hinges on how many subsequences are there? How many subsequences does an array have? All right? And so, how do we enumerate through all the possible subsequences? Well, let's look at an array. Let's say the array is equal to 1, 2, 3, 4, 5, 6. Okay? So, either the subsequence could be nothing, or it could be 1, or it could be 1, 2, or it could be 2. We ignore the 1. Or it could be 1. We ignore the 2 and then we go to 3. Or it could be 1, 2, 3, etc. Okay, so what are we doing here when we're generating all the possible subsequences? We're basically looking at each element in the array and deciding, is this element in the subsequence or is it not in the subsequence? And so when we do something like this, how many possible subsequences are there? Well, for each element in the array, there is a choice. There's a binary choice. Is this element in the subsequence or is this element not in the subsequence? Okay, so the number of subsequences is equal to 2 to the n. Okay? That is the number of possible subsequences, because in order to generate all possible subsequences, we go through the array, through n elements, and for every choice, let's say we include this, whether or not to include this element in the subsequences or not include this element in the subsequences, we multiply the number of possible subsequences by 2. Okay? Okay, so this for loop has 2 to the n iterations. So is that our running time, just 2 to the n? Not quite, right? Not quite, because we have this value here. We have this piece of code here. We have to check if the subsequence is increasing and if the size of this subsequence is less than the max. So this right here takes O of one time, right? This is a single comparison. But how long does it take to make sure if a subsequence is increasing? Well, we got to go through the subsequence one by one, each element, right? And make sure each element is smaller than the next, right? And how long could this subsequence be? Subsequence could be n elements long. It could, in theory, include all the elements of their original array, right? That's the worst case. So this here takes O of n work. Okay, so we got 2 to the n iterations times 2 O of n work, which means that the total running time is equal to O of n times 2 to the n. Okay, not ideal. I mean, I've seen worse running times, but not many worse running times. It's hard to get much worse. Although, of course, there are worse, right? But here's the good news. We are able to solve the problem, okay? And in computer science, that's not always a given. That you went through this earlier, in the earlier part of the course, where when you discuss computability, not all problems are computable. So at least here, we know this problem is computable, and we have an algorithm that computes the problem, okay? Positive spin. Negative spin is that the solution we've come up with is so incredibly slow that most of the computers we have access to probably won't be able to actually do this algorithm for any reasonable size of n. Okay? So we got to get better. We got to get better. And we got to get better. And so, could we find a backtracking solution to the LIS problem? Okay? Well, could we make this slightly better? That's what we really want. Well, let's say we wanted to do this recursively. Sorry. Yep, sorry. Just making sure I'm trying. Let's say we wanted to do this problem recursively, right? So what is recursion? It's reducing a problem to a smaller instance of itself. Okay, so can we reduce this longest increasing subsequence problem to a smaller instance of itself? Well, what if we go through each element in the array one by one? Okay, what if we say that either the subsequence does contain the last element of the array, in which case the longest increasing subsequence of the array 1 to n is equal to the longest increasing subsequence of the array 1 to n minus 1, because we're omitting this last element from the array, or this element, or the last element of the array is in the longest increasing subsequence. In which case, what does this mean? In which case, it's not so clear. We got to be a bit clever. But we know this. If the last element of the array is in the subsequence, it means that all the elements all the elements of the subsequence that come before it can't be larger than a of n. Okay? If we include a of n in our subsequence, it means it puts a ceiling on the size of the elements of the subsequent elements that come before it. Right? So if a of n is 1, 34, 30, if 30 is part of the longest increasing subsequence, it means that, and we put it in the longest increasing subsequence, it means that we can't put 34 in the longest increasing subsequence down the line. Okay, but maybe that's not a bad thing. Maybe 34 is not part of the longest increasing subsequence, right? But maybe it is. So that's why we have two cases. That's why we have two cases. We just want to see, we just have to consider both the case where 30 is part of the longest increasing subsequence and the case where 30 is not part of the longest increasing subsequence. And then and then recursively call LIS on the prefix of the array. Okay? So the search tree becomes something like this. Okay, I reduced the array a bit just to make the search tree more visible. And so we start off with nothing in the subsequence. And we say that x, the largest element in the subsequence, is infinity. This signals that we could add any element to our subsequence. Okay? So what do? We first go to the last element of A1 through 4, or A1 through 5. Okay? And we look, so over here we have A1, 2 through 5. And when we look, if we add 1 to SS, then we now have a subsequence that has 1 in it. But we also know that no more elements, any elements that come after this, any elements that come before this can't be larger than 1. So as we go through the additional prefixes of A, as we look at A1 ... 4, and as we look through A1 ... 3, we know that we can't add any elements that are larger than 1. And in this case, there are no elements larger than 1, and this is where our search tree ends. Okay? But let's say we decided to skip the last element of A5. Okay? And we did this. Now we have a choice. We could either include A4, which is 8, in the subsequence, or we could not include it in the subsequence. If we do include it in the subsequence, now our maximum value that we could add to the subsequence is 8. Great. But if we don't include it in the subsequence, then our maximum value that we could add to the subsequence is 7, which is also fine. Okay? So this is how the search tree works. We just keep track of the smallest element in the subsequence so far and make sure we don't add any more elements to the subsequence that are larger than that smallest element, making sure that the subsequence stays increasing. Okay, so in this way, we don't have to, at the very end, check to see if the subsequence is increasing. That O to the n amount of work, or the O to the n function, that's not necessary. All we need to do is go down the search tree. And hopefully record the size of each of these subsequence when the different branches of the search tree terminate. Okay, so this is what the algorithm looks like. If there are no elements in A, then we just return. Okay, but if there are elements in A, then we simply go and recurse on all the smaller elements. We simply recurse to see what is the largest element, what is the largest increasing subsequence for the prefix of this array. Okay, and then we determine if adding the last element to this subsequence would increase the size, or if it's possible, or if it's not. And then we output n. Okay, so what is the running time analysis of this? Well, we got a recursive call. Here, right? So that's not ideal. So this is the case where A of n is not added to subsequence. And this right here is the case where a of n is added to subsequence. Okay, so we got two recursive calls. So the algorithm is defined by the recurrence t of n is equal to, here, t of n minus 1 plus this right here. This is also t of n minus 1 plus t of n minus 1 plus, we could just say there's some constant amount of work due to these comparisons. Okay? There's not n amount of work, it's just some constant, just to keep the circuitry going. Okay? So we got a recurrence that's described by t of n is equal to 2t of n minus 1 plus some constant amount of work. So what is the solution to this recurrence? The solution to this recurrence, we could analyze the tree. We got n minus 1, n minus 1, n minus 2, n minus 2, n minus 2, n minus 2. And at each level, we got 1 work, 2 work, 4 work, etc. So this tree, the work is dominated by the number of leaves here. So we know that t of n is equal to 2 to the n is equal to O of 2 to the n. Okay, makes sense? So the new recursive version of LIS that uses backtracking. Remember, the backtracking part is present because at every step we are checking to make sure that the increasing subsequence, that the subsequence stays increasing. Okay, so this component here checks the backtracking part. We're minimizing the search tree thanks to that component. And so we know that thanks to this component, we are running in O of 2 to the n time. Okay? Now, a lot of you might be saying, well, that's not great. It's still 2 to the n time, which is large, right? Which is a high growth running time. But given that we started out from n times 2 to the n time, and we've come to 2 to the n time, we are making progress in the right direction. Okay? Never scoff at progress. As long as you're moving forward, you'll get there eventually. So we did something good. We did something good, but there's a ways to go. And the ways to go is dynamic programming, is memoization. Okay? And we will talk about dynamic programming in the next lecture. All right. Thanks, guys, and I will see you in the next one.